Like with limits and derivatives, integrals satisfy particular properties, basically algebraic strategies that you can use to think about ways of simplifying patterns. Like, for example, just like with limits and with derivatives, they obey what's called the coefficient rule and the rule for sums and differences. Essentially, if you have a multiplier within an antiderivative, like c times a function, you can pass that constant multiplier through the antiderivative, and that will be equivalent. Or if we had something like x plus x squared inside of an integral, you could split those apart as two separate integrals, whether they're added or subtracted. And there are reasons why this makes sense that we'll talk more about when we talk about areas in 4.2 and 4.3. But yeah, those are two rules for algebraically manipulating integrals. So let's try using a couple. So say we wanted to know the antiderivative of this polynomial or this nasty thing. So essentially, we could always start by breaking it down into parts. Now, essentially, the point of this rule is to realize you can do these one by one as long as you only swap the integrals to terms. But if we were to write it out carefully, what we'd have is the integral of x to the fourth with respect to x plus the integral of 4x cubed with respect to x minus the integral of 6x squared with respect to x. And this would be equal to this up here. Also, one thing that it's easy for students to forget is that you need to put, if you're going to break an integral into parts, you need to write dx at the end of each one. You need to kind of split up the symbol, which kind of indicates antiderivative, and the dx is needed at the end of each component. Because if you really look carefully here, we have the antiderivative of a combination of things with a single dx, and that dx splits into parts. It's sort of like factoring. And you need to make sure to write this dx or else it's not correct notation. And it technically doesn't make sense if you don't. But it's a little weird if you've never worked with integrals before. So that's, just why I'm saying be careful. But how I kind of imagine it is I have three terms in here. You can split up integrals based on adding or subtracting. Also, if we have a coefficient such as 4 or 6, you can pass those directly through the integral. So I could rewrite this as, well, integral of x to the fourth dx plus 4 integral of x cubed dx minus 6 integral of x squared dx. And now I could directly apply the power rule to each of these, the reverse power rule. So now, again, be careful to not use the derivative rule, but the integral rule instead, which says add one and drop the reciprocal, just as we were practicing. So here I should have x to the fifth over 5. Then this one would be 4, and x to the fourth, I would add 1 and drop the reciprocal, so I'd have plus 4 times 1/4 x to the 4. And then with the last one, this one is x squared, so I have 6 times x cubed over 3. And also, another thing is when you're splitting your integral up, and you might be wondering, well, what about plus c? Remember I said this in class on Monday, but c is an arbitrary constant. It does not matter what it is. And if, say, you had 3 different integrals, technically you could think every single one of those needs a plus c on them. But all of those c's represent an arbitrary constant. So if you are solving an integral with multiple different, an antiderivative with multiple different steps or multiple different integrands, integrand is just the name for the inside kind of each integral. Then you just need a single plus c at the end. And, I think I said this, but what I recommend is when doing antiderivatives, just solve it and then add c at the very end. Don't worry about it till the last step. And of course I could clean this up because, well, 1/4 divided by 4, that will just cancel and leave me with just 1. And 6 divided by 3 is 2. So I would have 1/5 times x to the 5 plus x to the 4th minus 2x cubed plus c, and this would be my simplified antiderivative. And as always, I could check my answer by taking the derivative to make sure. But notice, well, if I differentiate, the 5 will drop and cancel out. So I would just leave x to the 4th, perfect. Derivative of x to the 4th is 4x cubed, perfect. And then derivative of negative 2x cubed is negative 6x squared, perfect. Derivative of c, 0. Again, I always recommend checking your antiderivatives until you're starting to feel more comfortable with each of the rules and each of the steps. Now looking at the second example, notice here I have division, and also notice that it never says that you can divide across the top and the bottom separately. So like I did over here, you can't split up the integral on the top and bottom. That will not work at all. But what we could do in this case is use algebra, since all of this is divided by x squared. Technically, just each term should be divided by x squared. So what this would leave us with is I'm not going to separate the integral out first, but what I'm going to do is just going to split up the denominator. Because it's a common denominator, I am allowed to split it. I sometimes like to call this the splitting rule, because I found that a lot of students from algebra they learn how to combine fractions when they have a common denominator, but they forget that if there is a common denominator, you can also split it up should you need to. And the reason why this is helpful is because now I can simplify these and rewrite them as powers, because this first one is 4 over x squared. Well, that I could write as 4x to the minus 2 with respect to x. And then we could go ahead and split them up as well. So this would leave me with negative integral of, well, 5x squared over, or 5x over x squared. One of those x's would cancel, and that would just leave me with 5 over x, which would be 5x to the minus 1. Then moving on to the third term, x squared would cancel, so this would just leave me with plus the antiderivative of 2. And then looking at the last one, x cubed over x squared is just going to be x. And notice how as I split them up into 4 parts as we can, and I made sure to write dx at the end of each. Also, technically, you don't have to split them up. The point is you can do them individually. Like each of these integrals could be solved in 4 parts. And like, again, technically I could have skipped all of this work if I just applied the power rule from square 1 to each of the terms and sort of like ignoring the coefficients. And notice you could also extract these coefficients, like pull the 5 there and pull the 2 there and pull the 4 there. But you basically, you don't need to. That's the point of the rule. Just knowing that it will always work. So for x to the minus 2, I would add 1 and drop the reciprocal. So that would be negative 1 and times negative 1. So I'd have negative 4x to the negative 1. Then moving on to the next one. Also, remembering about x to the minus 1. This is one where actually you can, if you think about using the reverse power rule, this is the one case where it does not work. Remember I said this in class. The reverse power rule does not work for only the power negative 1. And this is because actually we have a different rule for how we deal with a divided by a single x. And this is an easy one to mix up, because if you recall, if I have something divided by x, that antiderivative is the natural, we call the natural log rule, or the antiderivative of 1 over x is the natural log of the absolute value of x. So here, again, I could pull the 5 through, which would leave me with 5, and that would leave me with 1 over x, whose antiderivative is the natural log of x. And this one should be subtracted. My apologies, because I can see there's clearly a subtraction sign from the original. But anyways, just the power rule you can always use for anything except for a divided by a single x, which is the case with this one. Now moving on to a constant, the antiderivative of a constant is just x, so 2x. And then the antiderivative of x, I can use the power rule, because again, I can think of that as x to the first power. So I would need to add 1 and drop the reciprocal, so I'd have plus 1/2 x squared. Again, I would also need a plus c at the very end. And of course, I could rewrite this, in a different order or whatever, write x to the minus 1 as 4 divided by x. But that's good enough for this example. In the next video, we'll talk about how do you solve for c? Like if we could figure out what c is, what number is that? How do you do that? Let's look next video.